Hello kids, and welcome to another video lesson by your teacher. I'm actually pleased. I think this lesson usually takes me, I'm usually crunching to get all of this information into one class period, and I feel like I always have to rush a couple of these things. So I'm not disappointed to be able to, even though I'm disappointed not to be with you, I am not disappointed to be able to kind of go a little bit slower through this. So in your notes, you are starting Unit 5, and the name of the unit is Polynomial Functions. Now in truth, linear functions are polynomials. You don't understand how much you love polynomials, right? There's so many good things and so much good math about polynomial functions. Linear functions are polynomials, and so are quadratics. And you've spent a lot of time with lines and quadratics, right? Algebra 1 should have touched on lines and quadratics, even more so than they do, in my opinion, of course. And then in Algebra 2, we did a lot more lines, and we just did a lot more with quadratics. So the purpose of this warm-up is to review a couple of things about these polynomials, right? A linear in the family of polynomials are linear functions. The shape of the graph is a diagonal line. Remember, not a horizontal or vertical line, a diagonal line. And remember, a linear function is y equals, I know we usually call this m, but let's call it a x to the first, dilation factor x to the first plus b. The degree, the highest degree on the independent variable is 1. Solutions. When I ask for the number of solutions, remember, you can tell me real or non-real. How many real and non-real solutions does a linear function have? 1. It's not a coincidence. Now, X-intercepts, remember, X-intercepts must be elements of the real, must be a real number. How many X-intercepts does a linear function have? 1. How many extremes? Extremes mean turning point. How many turning points does a linear function have? 0. A linear function either increases or decreases, right? It does not do both. Concavity, you don't know what concavity means yet, right? You don't know what that is yet, but I'm going to give you the answer. None. A linear function has no concavity, and I'm not going to define concavity yet for you. Another type of polynomial is a quadratic. What's the shape of a quadratic, though? Let me change my color for quadratics. A quadratic opens up or opens down, and these are polynomial functions, right? What's the degree of a quadratic? Dilation factor, independent variable squared. Right? The degree of a quadratic is 2. The number of solutions. Every quadratic has 2 solutions. But how many x-intercepts are there? Right? There might be 2, or there might be 1 that we call a double, or there might be none x-intercepts, right? But there are always 2 solutions. What about extremes? A turning point, a max or a min? Every quadratic has 1 max or 1 min. And what further can you say? Since there's only 1, it is the absolute max or min. Now, what about increasing or decreasing? right? Unlike a linear function does both, right? Increases and decreases. Concavity, again, I'm not going to define this for you, but I want you to write this down. Always concave up or always concave down. Now, I want you to compare some things here. A first-degree polynomial has one solution and one x-intercept because this solution is real. A degree 2 has two solutions and at most two x-intercepts. A degree 1 polynomial has 0 turning points and no concavity. A degree 2 polynomial has 1 turning point and is either concave up or concave down. Let me tell you some things about a cubic. A cubic function is dilation factor times independent variable to the third power. And then I decrease my power, second power, first power, 0 power. The shape of the graph is something I call a snake. What's the degree of a cubic? The highest exponent you see on the independent variable is 3. Using the pattern of linear and quadratic, can you guess how many solutions a cubic will have? 3. So at most there will be 3 x-intercepts. Remembering x-intercepts have to be real numbers. Since there are 3 solutions, there can be at most 3 x-intercepts, but there might be 2 where one of those is a double. Or there might only be 1. Look at the extremes. A degree 1 has 0 extremes. A degree 2 has 1 extreme. Can you guess about a degree 3? That's right. It has at most 2 turning points, both a max and a min, or something we call a plateau, or something we say is neither. All of these things we kind of still have to, right? We don't know what a cubic is yet, really. So I'm just giving you this information ahead of time. Increasing or decreasing, cubic functions might do both, or they might only increase, or they might only decrease. Crazy, huh? Concavity, every cubic function has both types of concavity, concave up and concave down. Notice for quadratics, every quadratic both increases and decreases, but only has one type of concavity. Right? So a cubic function is also a polynomial. Polynomial functions is a very, very large family. Linear functions are the first type of polynomial, quadratics are the second, and cubics are the third. Your homework is to graph cubics. You do want to use your calculator. graph all axial intercepts, right? I used that from the IB problem. That means both x and y intercepts, but you can use your calculator to find them. I will teach you how to find something called a point of inflection. And I want to ask you to color the concave up and concave down intervals, but I will teach you how to do that. All right, move to notes, and you have a handout to go along with this. Whoa, look at that. Sorry. I go get a drink of water. Okay, this is, right, look at polynomial functions. All those A's are coefficients, and they have subscripts. N minus 1, right, all the subscripts. And notice that it ends with a constant. Notice that the highest degree is n, and that the degrees on the independent variable x go down from there. To be a polynomial function, by definition, the exponents must be positive integers. I can have negative integers. I can have 0 as an exponent. That's fine. You just can't call it a polynomial. Now, you will find some books that call constant function polynomials. We're not going to have that argument. So just some vocabulary. The degree is the highest exponent on the independent variable. X-intercepts are real solutions. It's when you make y equal to 0 and you solve for x over the set of real numbers. You have at most n x-intercepts. So if you have a degree 10, you might potentially have 10 x-intercepts. Extrema are local or absolute max and mins. Whoa, what is that formula? It kind of looks like, don't say it, don't say discriminant. It's not a discriminant. That is not a piece of the quadratic formula. It has no special name because it's not used as often as the discriminant. For this unit, you need to remember b squared minus 3ac has something to do with extrema. You have at most n minus 1 extrema. So think about that. If you're a degree 1, how many extrema do you have? 1 minus 1 is 0, no turning points. If you're a degree 2, how many extrema do you have? 2 minus 1, you have 1. If you're a degree 3, how many extrema do you have? At most 3 minus 1, or at most 2. You cannot have more turning points and be a cubic. The domain of all polynomials is all real numbers. Polynomials are always continuous and they're smooth. They have no sharp points like absolute value, and they are never ever constant. And the reason I say that, sometimes, be careful, your calculator, a calculator sometimes makes a poly look flat or straight. You need to understand, and it really just comes from number sense, right? It really just is a numerical domain range issue. That's a little deep right now. You just need to know that polynomials are never flat. They're never vertical. They're never horizontal. They are never vertical. I don't know why I put an apostrophe there. Degrees and x-intercepts, right? They are related. It's not a coincidence. Oops, sorry. b squared minus 3ac is something that you're going to want to use this unit a lot. More vocabulary. Okay, here's where I'm going to define concave up. And yes, that's a soup spoon. I think of concave up as soup for you. I don't know how many of you know Seinfeld and know the Soup Nazi, but it's a great episode. and he would always, the owner of the soup store would always determine if he liked you or didn't like you, and if you wanted soup, the best soup in the city, and he didn't like you, or he did like you, he'd say soup for you, and if he didn't like you or was mad at you, he'd say no soup for you. So when I think of a soup spoon, I kind of think of this ladle, and you see how this curvature right here, almost also if any of you have contact lenses, right? It's like the shape of your contact lens when it goes into your eye, right? I call that soup for you. If you put that ladle down into a bowl of soup and pull it back up, you get soup. Soup for you. In reality, on a polynomial function, these are the two shapes, right? This one, this little shape is increasing, but concave up. This shape is decreasing and concave up, right? Do you see the soup spoon? Soup spoon, soup spoon. Concave down is a soup spoon the wrong way, right? Do you see that? If you put this spoon down into a bowl of soup and then back up, you get no soup for you. On a polynomial, increasing and concave down, decreasing and concave down. To me, that's a soup spoon the wrong way. Soup spoon the wrong way. So when you think concavity, think curvature, right? Curvature. A linear function has no concavity. It's straight. A parabola is either always concave up or always concave down. Other polynomial functions sometimes do both. And when they do both, just like when, think about a parabola. Think about a parabola that opens up. A parabola decreases and then changes direction to increases. What do you call that point? When a parabola opens down, it increases and then changes to decrease. And you call that, right, that place where it turns around? That place where the parabola turns around, you call the vertex. Changes from increasing to decreasing, you call that the vertex. Well, what about where a function changes curvature from concave up to concave down or vice versa? That's called a point of inflection, or poi. Poi, which is actually in Polynesia, that was a staple food, right? That was kind of like the starch of Polynesia. It's ground up ginger root, I think, and it tastes terrible. It's like paste, like glue, unless you put a bunch of sugar in it. Then it tastes awesome. Or you can bake bread with poi, and it's the chemistry of what the ginger root is turns the inside, like the outside of the bread looks brown like a crust, but the inside is this really pretty purple. It's awesome. It's called poi bread. Yes, I spent many summers in Hawaii, teaching in Hawaii, actually. It was really cool. So, a point of inflection. Where does a function change from, just like a parabola when it changes direction, is at a vertex? Well, what about when you change from being concave down to concave up, right? Concave down to concave up. Or concave up, see that curvature? To concave down. That point there where you don't change direction like a vertex, you change curvature. Concave up, change, concave down. So that point is called the point of inflection, and there are at most n minus 2 points of inflection in any polynomial. So what about a degree 1? You can't have negative points of inflection. That's nonsense. How about a second degree polynomial? How many changes in curvature does a quadratic have? 0, right? A parabola is always concave up, always soup, or always no soup. But a cubic function always has one change in curvature. There's the formula for finding what? The x-coordinate of poi. Doesn't that kind of sort of look familiar? Negative b not over 2a, but negative b over 3a. 3, think cubic. And then how do you find the y-coordinate? If you know the x-coordinate of poi, how do you find the y-coordinate? Plug it back in. Find your polynomial and put this number into it, and you get the y-coordinate of poi, where you change from soup to no soup, or where you change from no soup back to soup. Every cubic will have one point of inflection. Every single one of them, just like every single quadratic has one turning point. Every cubic has one point of inflection. All right, so here is a table of values. You don't need to write these table of values down, but I want you to get your calculator out, and I want you to put these values. Actually, don't. Don't. Never mind. I'm going to draw this for you. But what if I did? I put these into L1 and I put these into L2. Now I want you to look at this discrete data. What's happening to x? Negative 3, negative 2, negative 1, 0. What is x doing? Increasing, right? What's y doing? Y starts at negative 34 and jumps very quickly. Look at that. From negative 3 to negative 2, you went all the way from negative 34 to 0. Man, that's a big leap. Ooh, 0. Hey, what's this? It's an x-intercept, right? When x is negative 2, y is 0. Hey, look what happened here. What's going on here? Polynomial functions are never flat. So if at negative 1 you were 14, and at 0 you were back at 14, something had to happen. Then I go from 14 back down to 6, and then at 2, I was negative. When you're a continuous function, which all polynomials are, and you change from positive to negative, what must be here? There must be another x-intercept if you change from positive to negative. Then you go more negative to negative 10. Wait, then you come back up. What must be here? A minimum, right? If you were at negative 10, and then you come back up to negative 6, you had to turn around. Oh, what does that mean up here? There must have been a maximum, right? Now, oh, what happened again? All of a sudden my ranges went from negative to positive. What must be true here? Another x-intercept. So how many x-intercepts are there? 1, 2, 3. How many solutions does a degree 3 have? 3. And in this case, all 3 of them were real. And then notice at 5 I was at 14, and at 6 I'm way up at 56 again. Whoa. All cubic functions have the shape of what I call a snake. Not a straight diagonal line, not a U, but a snake. Every cubic function is degree 3. The number of x-intercepts, remember, are real, at most 3. The number of extrema is 3 minus 1, n, right? This is n. 2 at most. Points of inflection. Every degree 3 has 3 minus 1. I'm sorry, 3 minus 2. So 1 point of inflection, and will both be concave up and concave down. Every cubic function. So there's my data. Do you see the x-intercept at -2, 0? Oh, hey, I had a y-intercept, didn't I? When x is 0, y was 14. Do you see it? And then look at what this is. That must be a maximum. Then as you see x continue to go, the domain and to increase, here is 1, 6, and here's 2, -4. So there must have been a what here? An x-intercept. Then my x values are negative, more negative, and then back up towards 0. So there must have been a min somewhere around here. Y values were negative, y values are positive, there must be an x-intercept there. The domain is all real numbers, so I suspect that this is going to keep going up, and on the left here that I was always rising here. Can you see curvature? What does this snake look like it is first? Concave down, right? So there's the graph, right? When I drew the actual, here's the function, x cubed minus 4x squared minus 5x plus 14. There's the y-intercept, right? When you plug in 0 for x, you get 14. (14) is the y-intercept. There is a local max. Because of the domain, that is not an absolute max, right? There is no absolute max. This keeps going forever. There's no more turning points, right? Because I can only have at most 2 turning points. And I've got 2. There's the local min. I know because of the data, one of my x-intercepts is, oh, that should say -2, shouldn't it? (2, 0). I don't know these other 2 x-intercepts, but I know their y-coordinate is 0. Can you see where the function changes from concave down? This is no soup for you. No soup for you. No soup for you. And then somewhere around here, I change from no soup for you to what? It's not very bright. Soup for you. See that? Right here somewhere is poi. I marked poi with a star. You don't have to. But a point of inflection has an x-coordinate and y-coordinate. How can I find it? Like that. So how do I find the x-coordinate? I go to my equation. This is ax, right? Ax cubed minus bx squared minus cx to the first plus d. So the x-coordinate of poi is negative 4 divided by 3 times 1. So that's 4/3. Now, go ahead and put this function into y1. I said don't bother doing the data, discrete data. But please put x cubed minus 4x squared plus minus 5x plus 14 into your calculator. Do not hit graph, because probably, right, you'll be on a Zoom 6 window, and what's your y-intercept? Right, your y-intercept is 14, so you have to make your y max go to at least what? Right, make your y max go to, I don't know, 20, 30, something like that. And look at the snake. Right, you see the local max and the local min. You might need to make your y min go a little bit lower too, just to really get the local min on your screen. So you know the x-coordinate of poi is 4/3, so hit trace 4 divided by 3. And look at your cursor. Doesn't it look like that's where no soup to soup changes? Remember, this is concave down, and over here you're concave up. And this point is where you change from concave down to concave up. And that point is 4/3, comma, did you get about 2.6? Okay. We don't know how to find these yet, but they are real numbers, right? They are x-intercepts, and I see 2 of them. And it is, both of them are real, along with the -2, comma 0. All right. Next. Oh, what's that? Oh, nice. So there's my concave down interval, right? And that's from the left side of the domain to the x-coordinate of poi. And here is my concave up interval from the x-coordinate of poi all the way to the right side of the domain. That should sound a little bit familiar, right? All right, so let's make some generalizations. And let's investigate with our calculator. Every cubic has 3 solutions. They all have 3 solutions, but they have at most 3 x-intercepts. Remember, x-intercepts have to be real. Solutions do not have to be real. How many x-intercepts did this polynomial have? The one that's on your calculator, the one that we were just dealing with. 3, right? So a cubic function is where the degree is n. I'm sorry, the degree is 3. 3 solutions, 3 x-intercepts. Change your y-intercept to 25 and look at that graph. Don't zoom in because I don't think the numbers work out quite right, but I just tried to make a trying to make a little bit of a, you know, just a little bit of a visual. Can you see what I mean? Look at that local min. What does it look like it's doing? Right? All I did, now remember, you know, I didn't change anything about that polynomial but shifted it up 9 units. No, 11 units, sorry. I still have 3 x-intercepts, but I will say that I have one, what I'm going to call crossing x-intercept, because you actually cross the x-axis, and then you have one what? Double x-intercept. So how many is that in total? Truly, isn't that still 3 though? Because you have one crossing x-intercept and one double. Think of it as kind of like mwah, kissing the axis, right? It just comes down, mwah, kisses it, and goes back up. Right? And it kind of looks like the vertex of a parabola. But it's not a parabola, because to be a parabola you have to be a degree 2, and this is degree 3. All right, now let's look at another cubic. This cubic has 3 solutions. It's a degree 3. It has 3 solutions. But how many x-intercepts? Can you guess before you even type it in? I'm just going to shift it up further. How many x-intercepts does it have? 1. So if you have 3 solutions but only 1 x-intercept, what must be true? There are 2 non-real solutions. Ooh. Ah. Kind of crazy, isn't it? Gee, I wonder how we would find those non-real solutions. And that's for another day. That's for another day.
I really got me.
Now notice I haven't done anything with the dilation factor, right? I haven't. I've done nothing to our original cubic, just moved it up. Hey, question. Could you foresee any cubic function that has 0 x-intercepts? For instance, what if I made that y-intercept 30 million? Would you ever have no x-intercepts? No, right? It's not possible because of the D word, domain. Domain. The domain's all real numbers, and you started off low and you ended up high, and you're a continuous function. Therefore, you have to have at least 1 x-intercept. There's more of the stir fry over there.
I know.
All right, next. Oh, sorry, I had a big conclusion there. Wait a second. So cubic functions have 3 solutions, but may have 3 x-intercepts, 2 x-intercepts, where one of them is a double, so you still really have a total of 3, or 1 x-intercept, where 2 are non-real. You will never have 0 x-intercepts on a cubic function. Right? Now, here's that b squared minus, not 4, but 3 AC. Has no name. We can name it whatever we want. Let's call it Dylan.
Oh, yeah.
B squared minus 3AC is a Dylan. So when you compute a Dylan for the first polynomial, b squared minus 3 times 1 times negative 5. That's 16 plus what? 3 times 1 times 5 is 15. And a negative times a positive times a negative is 15. I don't actually care the value of that. All I care is it's positive. So when you go back and change that, right, go back and change your y-intercept to 14, right, down here, because we're now here. Change the y-intercept back to 14. How many extrema did you have? Remember, every cubic function has n minus 1 extrema. And this one has what? 2 distinct extrema. 1 local max and 1 local min. But now change your equation not just by a shift. Eliminate the squared term. And it's not just because I'm getting rid of the squared term. I'm also changing the coefficient on the linear term. Do you still see the concavity there? You still can see it, right? But look at that middle. It looks almost flat. It is not flat, but it is no polynomial is ever flat. Look at what b squared minus 3ac is here. Look what our Dilation value is. Whoops, sorry. It was back up here. Here. What is b? B is the coefficient of the squared term. Where's the squared term? Oh, what must its coefficient be then? 0 minus 3 times a times c. I don't really care that what, again, the numerical value is, but 0 squared is 0, minus 3 times 1 times 14, right? What is that? Negative? Negative, I don't care. Negative, I don't care. Negative. This has no extrema, right? There is no turning point. Now I want you to look at x squared plus 14. So eliminate everything but the cube. Right? B squared, oh, what's b squared again? Oh, 0, right? So 0 squared minus 3 times a times, oh my gosh, I'm such an idiot. Right? I hope you caught me on that. B squared minus 3 times a times c, this is not right. What did I do wrong? Can you figure out my mistake? 0 squared minus, right, this is supposed to be b squared minus 3 times a. This is right, but what is wrong with this? C is just 1, right? I still do have 0 extrema. What's true here? B squared minus 3 times a is 1, but what is c? So b squared minus 3ac is, our Dilation value is 0. But I still have 0 extrema. So I get when our Dilation value, our b squared minus 3ac is positive, I've got two distinct extrema. One local max, one local min. But here I've got two. I've got a negative and I've got a 0, and both of those are 0 extrema. Well, I want you to look at them again. Right? So look closer at, hit a zoom 6 window. Oh, no, it's not a zoom 6 window. You still have to have your y max go past 14. When you look at x cubed plus x minus 14 minus versus just x cubed plus 14, I agree that there's no turning points, but can you tell that one of them looks like they slow down for longer in the middle? Right? Can you tell? So one of these situations is where we say we have a plateau, and one of them is where we say we have neither. Which one would you guess? That's right. So I think you're right if you guessed. When your Dilation value, or your b squared minus 3ac, is negative, you have something we call neither. When b squared minus 3ac is 0, we say, and I don't like this word, but it's not mine, we say there's a plateau. Plateau means flat to me. The polynomial is never flat, but it appears like it's flat. So here, let me give you some more pictures. First, cubic functions may have two extrema. And that's when your Dilation value, or your b squared minus 3ac, is positive. Or a plateau, when your Dilation value is 0. Oops, I should have put this over here. Or something we call neither. I don't like these names, but I didn't make them up. When b squared minus 3ac is negative. So here is a general cubic polynomial, right? The dilation factor is a. The coefficient of the linear term. The coefficient of the squared and the linear term help determine where you've shifted right and left. And affect whether you have extrema or not. D is your y-intercept. Remember, the shape is a snake. Degree is 3. Solutions are 3. So here's why I call these a snake. Now these should all have arrows, right? Here is one type of cubic function, right? This cubic function, the first snake, has both a local max and a local min. The second snake rises very quickly and then slows down. I'm still increasing here, still increasing, but just slowly. And then whoop! Oh, I missed. Whoop! Increase. That's called, so this is 2 extrema. This is called the plateau, even though it's not actually flat. And then look at this one. I just made it more dramatic. You still see the curvature, right? You're rising super quick. Super quick. You hardly ever slow down. You only slow down for an instant, and then whoop, you keep going. That's what we call neither. This is all when the leading coefficient is positive. Notice that when the leading coefficient is positive, the cubic function starts low and ends high. Starts low and ends high. Starts low and ends high. Can you guess what happens when the dilation factor is negative? I still get 3 snakes, but I start high and end low. Start high and low. Start high and low. This cubic function decreases to a local min, increases to a local max, and then decreases. This cubic function decreases rapidly, slows down, decreasing slow, then decreases quickly. Plateau. This one decreases even quicker. It slows down instantaneously right here. Keeps going down. Each cubic function, whether the dilation factor is positive or negative, has one point of inflection. Every cubic function is either concave up or concave down. It is never flat, never straight. So the maximum number of x-intercepts is 3. Look at this one. 1, 2, 3. 1, 2, 3. But each one of these only has 1. Right? If you have a plateau or neither, you're only going to have 1 x-intercept. Here, depending upon your vertical shift, you might have 3 x-intercepts, or you might have a double, right? If the minimum or maximum goes to the x-axis. So you might have possible number of x-intercepts, 3, 2, where 1's a double, and 1. Extrema. Maximum number extrema is your degree 3 minus 1. Possible extrema, 2 or none. Right? You cannot possibly have one turning point in a cubic. Can you think about that? If you only have one turning point, you ain't going to be a cubic. What are you going to be? A quadratic. So again, look at b squared minus 3ac, our Dillon value. Right? If I'm going to name it, why wouldn't I name it Dillon? So our Dillon value for the first 2 snakes, right? Starting high, ending low, starting low, ending high, starting high, ending low. B squared minus 3ac is greater than 0. When you have this kind of flattening out, even though it's not truly flat, right? This really slow down, this period of slow decreasing, period of slow increasing, whether you start low and end high, whether you start high and end low, your Dillon value is 0. Or when your Dillon value is negative, whether you start high, whether you start low and end high, or start high and end low, and you have what we call neither, right? There's no slowdown. There's just an instantaneous spot of slowdown where you change curvature, right? And how do you find where you change curvature? Where a function changes from concave down to concave up, or vice versa. Notice when A is positive, you always start out, no soup for you. No soup for, oh shoot, I should have made that blue, huh? No soup for you. No soup for you. No soup for you. But when A, that's when A is positive. When A is negative, where's the no soup for you? No soup for you. No soup for you. No soup for you. Notice the soup spoon is very dramatic when the Dillon value is positive. When A is positive, the concave up, or soup for you, is second. Soup for you. Soup for you. But when A is negative, the concave up, or soup for you, is first. Soup for you. Soup for you. Concave up. Concave up. concave up. Cubic functions are never ever straight. They are either concave down or concave up. Where a function changes from concave up to concave down or vice versa is called what? A point of inflection. And every cubic function has at most, or has exactly actually, 3 minus 1, 3 minus 2, 1 point of inflection. Right? Can you see it? Blue to red or red to blue, point of inflection. For cubic functions, you have a formula to find the exact placement of poi. There's the soup Nazi. Look it up sometime. It's pretty cool. Where do you change from soup to no soup? Or from concave down to concave up? The x-coordinate of poi is negative b over 3a, and then you plug that value into the polynomial for x, right? You take this number and you plug it into the polynomial for x, and you get the y-coordinate of poi. All right? So for tonight's homework, when you're graphing, I want to clearly see concave up and concave down intervals. I clearly want to see maxes and mins if your Dillon value is positive. I want to see poi, and I want these things labeled, right? You have your calculator, so you can label your max and your min. You can label your poi, right? And make sure to put arrows on to indicate that you know the domain goes on forever and ever. All right? Have fun, and I will see you tomorrow.